I now call to order the Society's 2,466th meeting in what is now the 151st year since its founding on March 13, 1871. Good evening, everyone.
Good evening.
My name is Larry Milstein. I'm the president of PSW, one of the oldest scientific societies of Washington, D.C., dedicated to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends, including everyone here in the Powell Auditorium and the Cosmos Club, and everyone tuning in on Zoom and on YouTube to tonight's lecture by Francis Housen. The Society is grateful to the sponsors of the 2022-2023 lecture series for their support, the Policy Studies Organization in cooperation with the American Public University, and a generous sponsor who has asked to remain anonymous. And we're also grateful to the sponsors of tonight's lecture, PSW members Brett Magaram and Eric Innig. Thank you, Brett and Eric. I am pleased to announce the following new member, tonight's speaker, Francis Housen, whose interest will be clear in some small part, or maybe a large part, from tonight's lecture. We welcome him to membership. If you are not a member and would like to join PSW or support the Society, you can do so through the PSW website using the blue Join button on the upper right-hand corner of the homepage. We welcome new members and appreciate donations. So please, join now. All members are entitled to wear the PSW Science Rosette. The rosettes are $15 plus 90 cents in DC sales tax. They can be purchased online or at the rosette table in the back. But please note that rosettes must be picked up at a lecture at the Cosmos Club. Generally, PSW can't mail them to you because of tax accounting complexities, which are onerous since we would have to keep track of the sales tax rules in every state where we send them. Recording Secretary James Hewlin, who is visiting us today and gracing us with his presence from Salt Lake City, Utah, will now read the minutes of the 2,464th meeting and the lecture by Andy Rivkin and Andy Chang on DART. I've got the wrong one.
We're going to talk about Mark Clampin.
Yeah, what a mistake. Sorry about that. The 2,465th meeting and the lecture by Mark Clampin on NASA's astrophysics program. James.
Thank you, Larry. You go to 2,400 lectures and it's bound to happen. It's very good to see all of you in person. I'm pleased to be here. On October 21st, 2022, from the Powell Auditorium of the Cosmos Club here in Washington, D.C., streaming online via Zoom in the PSW Science YouTube channel, President Larry Milstein called the 2,465th meeting of the Society to order. He announced the order of business and welcomed new members. A member then read minutes of the previous meeting. President Milstein then introduced the speaker for the evening, Mark Clampin, Director of the Astrophysics Division within the Science Mission Directorate at NASA headquarters. His lecture was titled, NASA Astrophysics, Exploration, Origins, and the Physics of the Cosmos. Clampin spoke about the space missions that NASA's Astrophysics Division builds and flies, and the science goals for those missions. Those missions generally aim to learn how the universe works, explore its origins and evolution, and search for the life on other planets. NASA's astrophysics program is structured around the National Academy of Sciences decadal surveys, which recommend priorities for science observations. The surveys generally recommend a balanced portfolio of small to large missions, and each decade they recommend a flagship mission. In 1972, the decadal survey recommended the Hubble Space Telescope, which launched in 1990. The recommended purpose for the telescope was to understand the Hubble constant. Clampin said that in 32 years of observation, the Hubble Space Telescope has far exceeded that purpose and facilitated research unimagined in 1972. In 1982, the survey recommended the Chandra Space Telescope. Chandra's X-ray observations have helped scientists study protoplanetary disks, map out dark matter, and research galaxy formation. In 2001, the survey recommended building a large infrared space telescope that would become the James Webb Space Telescope, launched in December 25th, 2021. While other infrared telescopes are cooled with liquid helium, using that cooling process would limit the Webb's usable life. Instead, Webb employs an array of membranes that constantly shade the telescope and prevent the sun from warming it. In July, NASA released Webb's first deep field image. Clampin said Webb's image begins where Hubble leaves off, observing wavelengths as small as 5 microns. Clampin examined the image for the viewing audience, highlighting galaxies acting as gravity lenses to reveal globular clusters that may have been created as early as 500 million years after the Big Bang. The speaker then described Webb's search for exoplanets by observing transits in front of stars that dim their observable light and allow scientists to gather data about exoplanet atmospheres. In 2010, the Decadal Survey recommended the next large observatory facility that is now being called the Roman Space Telescope. At 2.5 meters, the telescope will be the same size as Hubble, but it will have the same powerful infrared detectors as Webb. Roman will have 100 times the focal plane of Hubble to conduct infrared surveys to facilitate research into the nature of dark matter and perform an exoplanet census. Clampin then used animations to explain how Roman will study baryonic oscillations, supernovae, and detect gravitationally lensed exoplanets. Roman is scheduled to launch in 2027. The speaker then discussed time domain and multi-messenger astronomy, which the 2021 Decadal Survey identified as an important area in astrophysics. It studies transient events in the universe using different kinds of measurements, or rather, messengers. One such messenger is gravitational wave astronomy that allows scientists to see objects from the very early universe, understand pulsars, and see what happens when stellar mass objects collide. Clampin described a 2017 observation of a massive collision, which scientists detected via gravitational waves, X-rays, gamma rays, and optical light. He said this observation caused a sea change in the understanding of how heavy elements were produced in the universe. There are approximately 5,000 confirmed exoplanets and 9,000 identified candidates. Most were detected by NASA's TESS and Kepler missions. The Webb telescope has now begun studying the atmospheres of those exoplanets for evidence of life. NASA's next objective will be to directly image an exoplanet. The speaker concluded by describing several of the mid-class and smaller Explorer missions in the Astrophysics Division mission portfolio. The speaker then answered questions from the in-person and online viewing audience. After the question and answer period, President Milstein thanked the speakers, made the usual housekeeping announcements, and invited guests to join the society. He then adjourned the meeting. The temperature in Washington, D.C., 17 degrees Celsius. The weather was clear. The attendance was 58 in person and 43 streaming, for a total of 101 live viewers and 491 online viewers in the first 2 weeks of posting. Respectfully submitted, James Heelan, Recording Secretary.
Thank you, James. Are there any comments on the minutes? Online members can submit comments or record Corresponding Secretary Robin Taylor at correspondingsec@pswscience.org. I don't hear any comments. Nobody? Okay. I'll accept a motion from a member to accept the minutes as read. I have several. Any seconds? If you already said the first, I don't know if you can do the second. I'll have to look that up. All members in favor of accepting the minutes as read? Aye. All opposed? The minutes are unanimously approved and will be posted to the website in due course, subject to any important corrections that come in over the web in the next few days or by email. Okay, we now turn to tonight's speaker, Francis Housen. Francis is a Vilas Research and Gregory Bright Distinguished Professor of Physics at the University of Wisconsin-Madison, where he has been a member of the faculty since 1972. He is the principal investigator of IceCube, the massive neutrino detector deep in Antarctic ice at the South Pole. In September 2017, IceCube detected a high-energy neutrino from the direction of a blazar called TXS 0506 plus 056. This was the first ever evidence of a source of high-energy cosmic rays whose origins have been notoriously difficult to pinpoint since they were discovered over 100 years ago. The IceCube Observatory's first observation of high-energy cosmic neutrinos was awarded the Physics World Breakthrough of the Year Award. Francis is an author on over 1,000 technical publications, co-author of the textbook Quarks and Leptons on Modern Particle Physics, and he has written and edited several other books. His essay, Antarctic Dreams, about the early days of Amanda, IceCube's precursor, was featured in the Best American Science Writing 2000. He speaks frequently at technical conferences, colloquia, and workshops, and often gives public talks, and speaks with the media as well. Among other honors and awards, Francis is the recipient of the Smithsonian American Ingenuity Award, the Balzan Prize, the Bruno Pontecorvo Prize of the American Astronomical Society, the IUPAP Yoda Prize, the Bruno Rossi Prize, and the IUPAP Homi Bhabra Award, and several honorary doctorates. I probably kind of didn't pronounce that correctly, but he is a fellow of the American Physical Society, and he was named a Vilas Research Professor in 2021. He is a native of Belgium, and he earned an MS and PhD in physics at the Catholic University Leuven. All questions will be held until after the lecture during the Q&A session. Francis, the stage is yours.
Thank you for this kind introduction. Let me try the other one. Help. Okay. It's a pleasure to be here. Thank you for the invitation. This is the menu for today, and it looks painful. You know, when you give the stage to a physics professor, this is what happens. So I'm going to first explain what a neutrino is, then what neutrino astronomy is, then what IceCube is, which is actually the first neutrino telescope. Then I'll show you the first maps of the universe, which, as you can expect, full of surprises. And then I'll show you what the first neutrino stars are. So what's a neutrino? Well, in high school you learned that nature is made out of protons and neutrons that make nuclei, and then you put electrons around it and you have atoms. That's absolutely false, because there is another particle, and this was realized a long time ago, because neutrons can change to protons. And they notice if I'm the neutron and it decays and the electron goes this way, the proton has to go that way. This is high school physics again. But they notice that occasionally the electron and the proton would both go that way. And that's not possible. And so the suggestion of Pauli, a theorist in 1930, was that there was a particle that they couldn't see, nobody detected it. That's where the name ghost particle comes from. And its only role was to save the laws of physics, energy and momentum conservation. And, you know, was thought maybe this is a theoretical concept or something mathematical. But actually, Ellis and Mott in 1933 saw the energy disappear in the direction of the neutrino. And so this is a classic technique where you demonstrate the existence of particles by missing energy. But you know, there were only 3 particles, and they couldn't imagine they had discovered another particle. So this was forgotten for some 2 decades until Reines discovered the neutrino again. And so that set off the idea then of neutrino astronomy. But so now, to complete this, the neutrino is part of this game. In fact, there are more neutrinos than any of the other 3 species in the universe. So, as I introduced the neutrino, it's kind of an agent that makes nuclear physics possible. So it appears everywhere where there's nuclear physics, in the early universe. When a star explodes, when the sun burns, there's a nuclear reactor at the center of the sun. It emits huge amounts of neutrinos. The Earth emits neutrinos. At Fermilab they make neutrinos. You emit neutrinos. And the important picture is the one to look at, is the one here. You see, that's a nuclear reactor. To shield from radiation, you put water over it, and you notice that water is blue. Blue water is made by charged particles coming out of the reactor. So when a charged particle goes to some clear medium like water, it emits blue light. That's critical in the rest of this story. Critical also in the rest of this story. I'm stuck again. Yeah. Is that the atmosphere produces neutrinos. There are particles called cosmic rays that bombard the atmosphere, interact with the nitrogen and the oxygen, make a nuclear reaction, and that nuclear reaction makes neutrinos. And also muons, actually, which, I mean, unlike most of particle physics talks, you only have to know 2 particles here, neutrinos and muons. So I'll keep it simple. But it's very annoying because my next subject is neutrino astronomy, but you realize if you look up at the sky, you see neutrinos all the time. It's like you point your telescope and there are clouds, except these clouds never go away. So, what's neutrino astronomy? Well, this is astronomy when you look at the sky at night, and not in Washington, D.C., but if you're in a better place, you can see the plane of our own galaxy. We live in a galaxy and there are sources nearby, and those we see first, and then in the background we see the rest of the universe. By the way, the big surprise in neutrinos, this is not the case. We see the rest of the universe first and then our own galaxy. In astronomy, they change the color of the light. So if you go to red light, very red light, then the universe looks like this. That's the microwave background. And so there are 411 photons per cubic centimeter, including in this room, but through the whole universe. Remember that. That will be important in this talk as well. Then you can change the wavelength of the light or the energy of your particles, this quantum mechanics, to bluer wavelength, and then the universe looks like that. And you see, this is very interesting. So by changing the wavelength and you look at the universe, you see new things. And things you have already seen, they look different. So you learn a lot. This is a very useful game. And so astronomers have played this game until they ran into trouble. If you go to bluer and bluer light at some point, when the energy of the photon is like 100 tera-electron volt, then the sky turns dark. We cannot do astronomy anymore. I am using this unit, which you see here, TV. At Fermilab, we had an accelerator, we still have it actually, that accelerated particles to to 1 TeV. So that's my small unit in this talk. So by particle physics standards, these are huge energies for photons and neutrinos or cosmic rays. In this talk, it's a small unit. But so another way to look at this, if you look at the universe from microwaves to gamma rays, and I here added a picture of X-ray universe, you see it looks different again. For most of this region of colors, you can see the whole universe. But here you reach this demarcation line and the universe turns dark. And so the idea, as soon as Reines discovered the neutrino in 1956, was that you could study this universe with neutrinos. And that's exactly what we started to do. And the question is, this is like the dark side of the moon. What if there's nothing there? And believe me, I had to answer that question. Well, there is something there. The cosmic rays that hit the atmosphere and make these annoying neutrinos, they are observed in this energy range or this color range of the universe. Now, first, why does the universe turn opaque? That's very well understood physics, and I've already explained it. Because suppose you have a source very, very far away, and it emits a gamma ray, it's moving through this microwave background of 411 photons per cubic centimeter. Inevitably, it will meet one, and then it will produce an electron-positron pair. Now, that's very annoying, because an electron and a positron are charged particles. Charged particles are bent by magnetic fields, by the magnetic field of the Earth, the magnetic field of the galaxy, and the magnetic fields outside the galaxy, which we know very little about. And so that's the end of astronomy. However, what about the protons? Well, they are charged as well. I will call cosmic ray protons, some are helium and so, but that's a detail, doesn't matter. So they are charged as well. So they can be produced over there, but arrive from that direction. So the sky is scrambled, and they contain no astronomical information, so far at least. Neutrinos don't have that problem. Neutrinos, remember, they are ghost particles. You couldn't detect them really in 1933. So as they don't interact with anything, including your detector, most of the time, they reach you from the beginning of time and from the edge of the universe. So they are the perfect astronomical messenger, except they are very difficult to detect. And that's the problem we are going to solve. So why is it so important to know the sources of the cosmic rays? Well, two answers to that. They were discovered in 1912. And here we are more than a century later, not knowing where they come from or how they are accelerated. That's one answer. The other answer, half of my career I was a particle physicist, and so at CERN now we have beams of 14 TeV, again this unit, 14 times the Fermilab energy. But like in 1991, a modest experiment in Utah called the Fly's Eye detected this particle of 300 million TeV. And if you are a particle physicist, that was it. You could never put this out of your mind again. So what did we have to build to figure out where this cosmic ray came from and how it was accelerated? Well, a square kilometer telescope, that's the answer. But you don't detect neutrinos with glass. That's the problem. How to detect neutrinos is very well known. You need water and light sensors, photomultipliers. And this is a picture of an experiment in Japan, in the Japanese Alps. And you see it consists of 10,000 light detectors, which you see on the wall here. And the water is being filled in the detector. And these are the graduate students cleaning the photomultiplier tubes. So, the theorists in their wisdom, studying this cosmic ray problem, told us that experiment is 10,000 times too small. What do? You build one that's 10,000 times bigger. And so the idea of how to do that goes actually back to a meeting in Rochester in 1960, where Markov suggested the following method. So this is the cartoon of what Markov said in his previous in the previous slide. You go deep in the ocean where the water is clear, and you build a detector out of an imaginary kilometer cube of water. You fill it with light sensors, just like in the Japanese experiment, and then you look through your feet. You wait for a neutrino to come through the Earth, and what does this neutrino do? It goes right through your detector. But about 1 in a million times, it will actually hit a nucleus in the water head-on and make a nuclear reaction. And that what happens in the water is what happened on my picture of the nuclear reactor. The water turns blue. And if this... And so you detect the blue light. That's why you need the light sensors. And you see here, if this is a muon neutrino, a minor detail, neutrinos come in 3 types called flavors. But if this is one of the 3, it will make a muon. And this muon is a fantastic particle. It travels through the water for kilometers. And so if it reaches your detector, it speeds through it at the speed of light. And so you can detect particles very, very far away, beyond your detector. The other thing is, it travels at the speed of light or very close, but the speed of light in the water is 3/4 of the speed of light. And so that means it's like a speedboat that outruns the waves on the water, and it makes this bow wave. And that bow wave, if you map it, it gives away the direction the neutrino comes from. By the way, why do you look through your feet? You will realize later, if you look up, you get bombarded by muons, which have nothing to do with this problem. But that's, again, a minor detail at this point. So here is a picture of a neutrino going through a detector, except this detector is not under kilometers of water, it's under 1.5 kilometers of ice. And each of these little dots, these white dots, is a photomultiplier, is a light sensor, and you see the neutrino coming in from the left, it interacts, it goes through the detector, and you see the pattern of blue light made by this neutrino, and with your eyes you can tell what direction it came through. It came from 11 degrees below the horizon, so it came through the Earth. Nothing else comes through the Earth but neutrinos. So you know you have a neutrino, and you know where it came from in the sky, so you have a telescope. If you want to see the movie, I'll show that next. This is the same event. And we can reconstruct now this, the direction of the neutrino to 0.3 degrees. This is an achievement for physicists, but not very respectable for astronomy, but that's what it is. So this experiment was actually tried following the plans set out by Markov in 1960 off the coast of Hawaii. And these people developed a lot of the technologies that we use, but they failed, unfortunately. So we went to the South Pole and decided, I mean, the one good idea we had, the rest was basically luck, as I will explain, was that we realized that it was easier to freeze these light sensors into ice than to put them in the deep ocean with an unfriendly environment. That problem has been solved now, but still, it's still the case. So the experiment was actually built at the Physical Sciences Laboratory in Madison. And so then the logistics of this is that you fly your stuff or you send it by boat to Christchurch, New Zealand, where there is the logistics center of National Science Foundation. From there it goes by plane or by boat to McMurdo Station on the coast of Antarctica, a 9-hour flight in DC 130, and then it goes to the South Pole, another 3-hour flight. So at the South Pole, this is a picture. That's what you see. The South Pole is a desert. There's absolutely nothing. And, but for us, the important thing, you stand here on 3 kilometers of ice. And if you look, and we figured out, this took almost 10 years, that below 1.5 kilometers, this ice is incredibly transparent. If you look in the other direction, you see another important thing. You see the South Pole Station. This is actually what made this experiment possible. You couldn't afford trying this out and doing these deployments without the South Pole Station. And the other important thing about the South Pole Station is it's there at night working with people, about 50 people, over 2 will take care of the ice cube experiment that we built. So I cannot show you a picture of the ice, but if you go to the coast, you can imagine this is the Antarctic ice sheet, and at the South Pole it's 3 kilometers thick. And below 1.5 kilometers, there are no bubbles in the ice, and blue light travels for hundreds of meters. This was pure luck. We had no idea when we started. And in fact, for a long time, we didn't believe this ourselves, but it's true. So this is the clearest substance anyone can make. You cannot even make this in a lab. And the reason is this is 50,000-year-old ice. It's infinitely pure. And that gives it transparency. They now make water that has a transparency of close to 100 meters by purifying it. But, you know, in some places, the absorption length approaches 300 meters. So this is the picture of the NSF station at the South Pole, the National Science Foundation station. This is where the planes land. At that time, everything went in by plane. No other option. And this is the ice cube construction project at the other side of the runway. This idea existed long before we started building Ice Cube, and I want to remind you how modestly it started off. I mean, when I started this, I didn't have a lab, so I removed the ping pong table from a room I had and turned it into a lab, and we built the first optical sensors there. And you see the whole group in Madison consisted of 3 graduate students, a postdoc, and a respectable physicist. Bob Morse, who lives now retired in Hawaii. So the easiest part of the project are the light centers. You buy these from Hamamatsu in Japan at the time for about $1,000. And you put them in the ice. That's the concept. We actually built a small experiment mostly consisting of 500 photomultipliers that sit at a depth of 1.5 kilometers, and this was mostly to study the properties of the ice, and then we found these really surprising results, how clear it was. And the other thing we did, we detected neutrinos. Here you can see one. You've seen one before. This is the online display of what we call the Amanda experiment. And I can tell you, in the 30 years of this project, when I saw this event, this was by far the most exciting moment. It worked. And at that moment, we knew we could build a kilometer cube detector. No doubt about it. And you know, when I give the impression, this is not me. This was not easy in the beginning. Of course, then we do what you're supposed to do. You publish in Nature, make a lot of extravagant claims. We were helped by The Economist, who designed a logo for us of the Amanda detector you see there. And then you go off and ask for more money, more photomultiplier tube. This became industrial operation in the early 2000s. You see here the photomultipliers lined up. They are a bit bigger, but the concept is the same. And if you could go in the detector, this is what it would look like. You see this below 1.5 kilometers, you see these kilometer-long strings. And they contain 60 of these light bulbs. And if you go 125 meters away there is another string. And so 86 strings fill this volume. And once you have your stuff frozen in the ice, you have a completely stable detector that takes data uninterrupted even through COVID. So that's another picture, 5,160 light sensors. And the question you probably ask, and I will get rid of and then go back to physics, is how do you put photomultipliers in the ice? These are delicate things, right? Well, you need a power plant of 4.8 megawatt, which was made out of 40 car wash heaters. And you produce boiling water at 200 gallons per minute, and then you do the following thing. And this is now a proven technology that delivers a completely stable detector. The first 100 meters, by the way, is snow, and you just melt it. Then you bring in the hot water drill, which is a nozzle, and the nozzle puts out this hot water under pressure, and it falls by gravity. And after 2 days, it's 2.5 kilometers deep, so that you can put a kilometer-long string in the hole. There's never a hole, by the way. You just transform ice to water. The water circulates, and you reheat it, but it never comes out. So I think we've seen this before. Now you will see the hot water drill. It's delivered, the whole system is delivered like a circus string, except it's on sleds. This is the drill tower. This is the hose that's 2.5 kilometers long, built by a specialized company in Italy, in Venice actually. These are the car wash heaters, a bit improved by clever engineers. These are the generators that run normal fuel that come in by C-130 transport plane to the pole. And you see here the hot water drill is coming out. And so at the moment, there is a pipe of a volume of water that because ice is an insulator, it remains liquid for several days. You can move on now to another hole, but while this water, before this water refreezes, you have your light sensors present. You see they are in pressure vessels, and they have all kinds of electronics on them, which I will refer to later. And you see now you lower the cable that powers the photomultipliers in the hole. You attach one every 17 meters, instrument a kilometer-long string and let it sink to the bottom. And that's the last time you see your equipment, because once it's frozen in, it will never come out, of course. So here is a picture. I'm not making this up, you see. Here in December, January, 20 holes were instrumented, and you see the cables coming out. They go into this two-story building, and this two-story building contains the computers that reconstruct the light patterns and tell you what you are seeing. So I'll show you what you turn on the detector. What do you see? Well, you can all guess. You see the atmosphere, right? This atmosphere, the clouds that are always there. And so this is the detector taking data. You see, whenever you see a sensor light up in color, it detected light, and that information is used by the computer to reconstruct these muons. And you see, this movie is 10 milliseconds long. And you see all the muons that have been reconstructed. I can show it again. So we detect about 100 billion muons per year made in the atmosphere that make it to the 1.5 kilometers of ice. We detect 100,000 atmospheric neutrinos made in the atmosphere. And so in that mess we are looking for a signal from the cosmos. So when we finish constructing the detector, I cannot resist showing this slide. New Scientist put up a web page where you could bet on big projects. And we were only given a 6-to-1 chance to discover cosmic neutrinos. And I can tell you, I couldn't sleep the night I read this. And the Higgs was also given 6-to-1, and LIGO gravitational waves were given 500-to-1. And you know, we have seen all these things by now, so what wonderful time we live in. I could spend the rest of the day on this slide. I was actually not that worried, because this is a table that you can find in most elementary astronomy books. And it tells you that when you build a new telescope, you are going to see something interesting or do something interesting. And in our case, you know, we detect neutrinos that have 10,000 times the energy of those at Fermilab or more. So we could always do neutrino physics. That I was really never worried about. So that table, again, I could spend the rest of the hour on. So what did we do? Well, we started to look for the easiest thing possible. And that's the following. I explained how gamma rays, how, you know, the sky turned dark, except to neutrinos, at about 100 TeV, because the gamma rays transform themselves in charged particles. The protons, they cannot be used to do astronomy, but occasionally they are also moving through this microwave background. So occasionally they interact with a microwave photon, make a pion that then make a neutrino. And these neutrinos have incredible energy. The light pattern fills the whole detector. And so this is an analysis even a theorist can do, right? So we started looking for these events and didn't find any. But while we looked for these events, we found this one, which I'll show you next. And don't look for a muon track. This is one of the other flavors of neutrinos. So it makes an electron that makes a shower of light. And you see this big ball of light. And this big ball of light, I can actually tell by looking at it what energy this neutrino has. And it's too big to be produced in the atmosphere. The atmosphere produces a lot of neutrinos, but at high energy it runs out of steam. And it cannot really make those events. And we found two. And we didn't have the courage to claim anything. So what we went back to our first 2 years of data and looked for more of these events in an intelligent way rather than by serendipity. I won't explain what the intelligent way was, but here to reset your thinking here for a minute, this is this event superimposed on the data center in Madison. You see, this may be not a very sophisticated detector, but this event has the size of 6 city blocks. And so we detect, there are more than 300 signals in this event and more than 100,000 photons. And we know where each of them is to about 60 centimeters. So we're sure of the energy of these events. It has the precision of, real particle detector at Fermilab or CERN for these events. So we looked at the 2 years of data, we saw 26 more. And then we published in Science, and we were, as was mentioned in the introduction, the breakthrough of the year. All this happens in weeks. And we were very worried. You can imagine how worried, you're thinking all the time, what am I going to do? Is this not real? But it is real. We have now seen cosmic neutrinos in 4 different ways with incredible statistics. This is, you can ask the question, after all, you didn't use Markov's method of looking for tracks coming through the Earth. Well, we did. Some graduate student was still doing this, but we beat him by 6 months. So, but it was good to see his result. You see here, that's the number of neutrinos we see as a function of their energy. And so these are the neutrinos coming from the atmosphere. And then suddenly, at high enough energy, the atmosphere runs out of steam, and we see this excess of about 200 neutrinos per year coming from the universe. And so we are not looking actually really for a needle in the haystack. We are looking here for a haystack sticking out of the atmospheric neutrino flux. What did we see? Well, I show you a year of data here, 138,000 neutrinos. We know from our observations in this there are 200 cosmic neutrinos. So where are they? Good luck. Where do they come from? Well, you then go and just look at the high energy ones, the haystack, those that were in the haystack, and we looked at these in astronomical maps and did this for many years, and that led absolutely nowhere. Notice, however, we don't see the galactic plane in this map. There is no concentration of the neutrinos along this major axis of the ellipse. That's a very interesting problem, which is not in this talk. But the interesting thing we found out is this is a plot. The details don't really matter. This tells you how much energy there is in the universe in certain colors of light. And you see here is the microwave background. That are the most photons, that are the ones that make the universe obscure. Then you go through infrared light, visible light, X-rays. Then you come to gamma rays, and then the universe turns dark. But you notice this is our early measurement of the flux. There is more energy in the universe in neutrinos than in light. And that nobody expected. You know, cosmic ray physics and neutrinos was supposed to be boutique science, right? Well, neutrinos dominate the energy in So these are main conclusions. We don't observe our own galaxy, but we see a universe energetic dominated by neutrinos. And this is, of course, a real opportunity to do astronomy now. But I told you we were unsuccessful. So what we did is to find out where these neutrinos come from, we tried something different. Something brave. When we detect a neutrino at the South Pole, within less than a minute, we reconstruct it with just a computer farm. Normally, the neutrinos are reconstructed at the pole, then sent by satellite to Madison, further analyzed, and then sent to the collaboration for science. What we did, as soon as we knew the coordinates roughly, we sent information to every telescope in the world. And we had no idea whether anyone actually ever paid attention. But we just were trying just our best data overboard to the public. And this was an event, a very likely cosmic neutrino, 300 TeV. We detect in September 2017. And the event is shown on the next slide. And it turned out that you looked at its direction inside Orion, and it came from an active galaxy. An active galaxy is a galaxy like ours, except they have active black holes. I'll come back to that later. And the chance coincidence of this is about 1 in 1,000. So it's not a big deal. It's what happened afterwards that made this real. It was detected to be a galaxy, a black hole that produced TeV gamma rays, which is very unusual. It's a subset. So that made the plot thickens. In fact, we got our answer. At some point, 22 telescopes were looking in the direction of the neutrino event. And so one of them, an optical telescope, was looking at the event 73 seconds after the neutrino passed through the South Pole ice. And in fact, they saw a glitch in the source that associates this neutrino with that galaxy with a 50 sigma, for those who knows what that means. So they nailed the association of the neutrino. They only published this 3 years later, actually. It's very interesting. So we published this in Science. And, but you see there are 2 articles. The second article also contributed to make this a real event. You see here, after knowing where to look, we looked at the last 9.5 years of data. And what I've been talking about is this neutrino here, this little glitch. What we found in the archival data was this flare of neutrinos in 2014, which had all the right properties, right straight at the source, and all the right properties to be cosmic neutrinos produced by a supermassive black hole. So this is a picture of a rotating supermassive black hole, and there are many places you can accelerate neutrinos. And the most obvious place is this jet of particles it's accelerate. And I think people got carried away with this jet. We now think, we not only think, you will see later, that these neutrinos are produced very, very close to the black hole. And it's a region where there are a lot of magnetic fields. The accretion disk, the matter that swirls in, makes high magnetic fields. You accelerate protons. That region about the black hole is totally opaque. And so you have lots of gas and photons to produce neutrinos because you need a target to produce the pions that decay in neutrinos. So this is the picture that started to emerge when we studied this TXS 0506. By the way, 0506 are coordinates that is the telephone number. It tells you where it is in the sky. And TXS tells you what catalog. This stands for Texas, and it's a catalog of sources made by a Texas McDonald Observatory. So this is where my talk would normally end. But if you read today's Science, if I had been here yesterday, I wouldn't have been able to talk about this. But now I can, and if you read today's Science, I'm sorry, I'll tell you again what you read. But remember, the goal is still to find the 200 neutrinos in that map, which we couldn't do. But we wrote a physical review letter with our standard analysis, and we saw this active galaxy, NGC 1068, and it stood out in the map. And there were a few other sources that stood out in the map. And like in 2013, we didn't claim anything. We went back and tried to answer the question, are these fluctuations or are these real sources? And that's what we found the answer to and published in Science. I won't go in detail to what we did. Instead of reading this, just listen to me. What did we do? First of all, you know, for 10 years we had been doing Science. So we went back and totally recalibrated the detector, finding out where every phototube is, how it was oriented, and we calibrated every photomultiplier individually. So we knew its sensitivity to light one by one, all 5,000. And that was taken into account in reconstructing the data. And that refinement we applied to the last 10 years of data. Also, machine learning helps us to find the neutrinos. Now, I thought I was too old for machine learning. I thought I was very suspicious. God, it works. It does wonders. And so we could reconstruct the direction better, 0.3 degrees, as I mentioned. You know, this experiment was to have a sensitivity between 1 and 1.5 degrees when we started 15 years ago. And then the other thing, which was our telescope was partially blind because we described the direction. You know, you see this cluster of neutrinos of TXS. We described this cluster by Gaussians, and it wasn't Gaussian at all. So we had the wrong, what astronomers call point spread function of your telescope. So it means you're partially blind, because you have to have it right. Whether you over or underestimate it, you lose sensitivity unless you got it right. So I now enumerated several improvements. And so all this is done blind. It's done by a method that allows you to keep track of all the searches you do in the map. So what we put out after we unblind the data is a real probability. There are no unaccounted for trials. It's a real probability that what you see is not a fluctuation. And you will see there is the earlier result that we've published in physical review letters, and that has got us going on this. And then you see how slowly, with the improvements, the reconstructed neutrinos move toward the source, and instead of 40, we got 80. And so, of course, your confidence is proportional, more than proportional, to the number of neutrinos we see. And so we nailed this active galaxy, NGC 1068. You can look at this a different way, a bit more scientifically. In this picture tells you how many neutrinos there are in the direction that are coming from the background, from the atmosphere actually. But then when you approach the real direction of the source, you see the neutrinos increase. And what you don't see is that neutrinos also have on average higher energy, which helps to making sure that this is a real source. So another way of looking at, you see, here are the neutrinos that come from the source with the correct point spread function compared to the background. Then you see, this is, and I will stop there. You see here, this is the number of neutrinos, not as a function of direction of the source, but where they are in the sky. So you go through the southern sky, looking from the horizon to straight down or up, from the point of view of here. And so you test all these sources here, and they are at the level of our sensitivity. But here you see NGC 1068 sticking out. In fact, this is the line that gives you 5 sigma discovery before the trials. And you see it sticks out, but notice there's another source sticking out. It's our own old friend, TXSO 506. And though we don't use the time dependence, we just integrate all the data over 10 years, it still sticks out. So it survives this test as well. And there are a couple of other sources which I've listed here. The interesting thing about these sources is that they are all the same type. They have these very active galaxies that are hot and dense. And the fact that they are hot and dense means they don't emit photons. Not only is the sky dark in photons, these sources are dark in photons. And so this is totally the domain now of neutrino astronomy. So we are finally looking with a reasonable number of neutrinos to a region where this is happening very close to the supermassive black hole. So this was the dream of neutrino astronomy. One of the sources that's kind of second tier is NGC 4151, and that's interesting because 1068 and 4151 were the 2 first galaxies of this type discovered by Seyfert in 1943. He discovered Doppler lines that showed the rotating supermassive black hole. So here we are. Same 2 sources. I think I have already told you they all look like that, although this is an artist's conception. And so to conclude, the goal was, what are the sources of cosmic rays? Well, are it the cores of active galaxies? May be the answer, may not. Maybe there is a subtlety we're still missing. Maybe there are other sources that also make cosmic rays. These are all questions that remain to be answered. But I think the critical thing is that I hope to have convinced you that with IceCube and multi-messenger astronomy, we have the tools to solve this problem now. Finally, thank you very much. I didn't do this by myself. I think we have now 54 labs and universities in some large number of countries, listen there. But you see, these are my collaborators, and it's all these young people you see there who realize that machine learning works before me. Thank you very much.
So we have time for some questions. Many of you probably know the procedure, but some of you don't. So we have some microphones that have a blue windscreen or a red windscreen. Keep your hand up, and when the microphone comes to you, I will call on you by the color of the windscreen. And that's so the person in the back knows which mics to mute. So let's start with a blue mic up here. Please stand, tell us your name, and if you're a member.
Sorry. Hello, Matt Kaywood, new member. So with the help of machine learning, you were able to get to 0.3 degrees of resolution, but the detector events look very rich in information. So what is the theoretical limit of what resolution you could get from the detector, and what might you be able to see if you were to approach that limit?
Thank you for the question. I left one very important thing out. You realize it's the key is to understand the optics of that ice. Some things are it's easy. If there are bubbles, and bubbles, although this was not predicted either, disappear at 1350 depth, and so they are gone. But then the ice still it has crystal boundaries, it has some dust, and so you have to understand in detail the optics of the ice to reconstruct these events. And that's a problem that is ongoing. In fact, we are upgrading the detector in 25-26 season, and one of the games is to do a better study. It has other reasons for deployment, but one of the reasons is to deploy devices to yet better understand the optics of the ice.
Just quick follow-up, are the optics static or are they dynamic?
No, it's absolutely static.
Okay.
You know, for glaciologists, nobody had ever instrumented a glacier with a kilometer cube of sensors, right? So we have all kind of devices to do glaciology measurements, like the stability. You know, some of these photomultipliers have been in there for 15 years now, more, 17 years. And we have studied them. This detector is absolutely stable. And we don't see any changes. We have tilt meter measurements to see if the ice, when it flows off the Antarctic mountain range, whether it shears, and it doesn't as far as we can see. It probably does below the 500 meter, 400 meter below the last module. But yeah,
I should mention that online viewers, whether you're on Zoom or YouTube, you can also ask questions. The YouTube viewers, put your question in the chat box, and it will be read out loud. And Zoom viewers can ask their question by raising their hand. I'll call on you. Or you can type your question into the Zoom Q&A box. All right, so keep your hand up because it takes a while for the microphone runners to get to you. We have a question from the red microphone.
Stu Reuter, member. Two questions, actually. You mentioned the blue light in a reactor. I remember that as something called Cherenkov radiation, if I'm correct.
Yep.
My other question is, how much have you spent so far? If you can say that out loud.
Yeah. Actually, about 300 million.
Thank you.
And now that you ask, we actually have a method to make the volume of the detector more than 8 times bigger for the same amount of money. And so we have a design for that, which was submitted to the Decadal Review and endorsed by the Decadal Review. So, and that's the type, you know, I didn't emphasize this, but it's clearly, you need more neutrinos, you need better angular resolution, and that's what this detector will give you. Also, the detectors developed in the water have solve their early problems. And so there is now a detector being deployed in the Mediterranean and one in Lake Baikal. And there are designs for a detector in the South China Sea and one off the coast of Canada. So there are going to be more instruments, more neutrinos, better neutrinos. So this field is going to explode.
Blue microphone, Scott?
Yes, my name is Scott Matthews, and I'm a member. I remember when you guys announced the observation of Bert and Ernie, and I remember the just staggering energies of those particles. Is that characteristic of these cosmic neutrinos? Are you seeing lots more events?
Well, yeah, the answer, okay, I didn't go into I only mentioned, so the 88 neutrinos from this new active galaxy, they have typically lower energy. So these events were unusual. We found them serendipitously because they stick out with this huge energy. Now, that's not the way, however, to do this science. The way to do this science is try to come to lower energy where there are many more neutrinos. So we go from like 1 from the TXS source to 80 from this new source. And that, of course, is what makes it so convincing. There's also more information in it. We have information on the spectrum, which I didn't discuss. But I welcome you to buy science. I don't have any interest in it, but yeah. So you can do, so the game is to get more neutrinos, to get more information. Because things are happening so close to the black hole that it's challenging for normal astronomical telescopes. There are instruments like ALMA, there is radio that can look into these regions, but neutrinos are in principle ideal. We just need more of them.
We'll go to the red mic, then the blue mic, then we'll take something from the web.
Timothy Thomas, I am a member. I'm curious about neutrinos that may come from the Big Bang, and where are they? And what's the story with that?
Well, they are even harder to detect, and they have not been detected. There is a project to try to detect them. It's a very different subject than from this one. But you know, this being said, I think it's a great idea. And if I had an idea to detect them, I would detect them. But I am absolutely sure that I know everything about them. So in that sense, there's no room for surprises there. Or at least, maybe there is room for a huge surprise that would blow up all of cosmology. But that's unlikely. We understand these neutrinos just like we now understand the microwave background, to the extent we do. No, it's very difficult. It's totally different techniques. It's more like tabletop techniques.
I think we're taking a blue microphone,
Okay, Maria
and then we'll go
Zanarkova,
to the web.
a member. You had mentioned that neutrinos reach us from the edge of the universe and the beginning of time. Now, if you build better neutrino detectors, would you be able to extend the edge of the universe and move the beginning of the time further back?
No, well, eventually, you know, it's a good question, and it's something I didn't cover. You can do cosmology with these neutrinos. You can look for dark matter with these neutrinos. All this is another talk. So you should be happy that I'm not giving those tonight. But so what we are doing, when I make that statement, it's a bit in disappointment, because neutrinos, except for the fact they have this small mass, which doesn't matter in this talk, they're just like photons, they have physics that's not consistent with the standard model. Otherwise, they shouldn't have a mass. And so what we are hoping is that they don't reach the edge of the universe and the beginning of time, that we see actually effects of the new physics that's not in the standard model, which we use to analyze our data. And that's a bit of a disappointment, but we keep looking. With more and better neutrinos, that may come as well. We may make neutrino discoveries rather than doing astronomy.
Everybody should take note of the desire of physicists to disprove their own favorite and
Yes.
totally proved model.
Absolutely.
We have a question from the web, or a comment.
We have
Red
both
microphone.
a comment and a question. Carrie List says 300 million may sound like a lot of money, but it's the cost of a small NASA astronomy space mission today. And then we have a question from William Angel. The question is there a trade-off between directional uncertainty and energy uncertainty?
Not really. We try to get the best. There are different measurements, and we tried. If you have, the best reconstruction techniques, the best knowledge of the ice, then both improve. Then there is no trade-off. It's not. I wish we could give up on energy and get better angular resolution right now to look at that source. That's not possible. It's a good question.
Frederica? That would be the blue microphone.
I am Frederica Dorima, and I'm a member. Fascinating presentation. I was at the National Science Foundation. I was not of the people that funded you. There are a few other people from
Yes, I
NSF. We did not
recognize that.
funded you, but I funded many other projects which are very successful. I'm proud of that. But the biggest heroes, 300 million aside, are the researchers that are doing this work, fascinating work, and your talk touched upon many things. So I have many questions, but what in a sense I would like to know is, you said there are other observatories that are being planned, and somebody actually asked you earlier on if your measurements are dynamic, not static, and you said they are static, but in my view, it would be important to, in a sense, have dynamic ways of correlating measurements. And also, what new insights could be derived by, in a sense, correlating measurements from the various other observatories, neutrino observatories, given the astonishing speeds, all right? Actually, you mentioned the first example you gave was 900 million TV or 300 million TV. Number one, how did they measure that? What are the conjectures how it came? And then, of course, the measurements you're making are lower, in the 60s and the 100s, also high. So the opportunity for such neutrinos of going through multiple of these observatories are high. And so it would be a value to try to correlate these measurements. And second, what additional physics you can derive by having such?
These are a lot of good questions. I want to start with the question of multiple observatories. And, when I always struggled with that, because at the beginning, when we were starting the Antarctic project, we were sure, and we were sure, where we were right was that this was the way to have easy deployments and deploy a stable detector. And that we have delivered. And so, but while they were struggling with reviving the Dumont experiment, there was this discussion of, no, we should only build one experiment. And then you have to decide which the best is, which is impossible. By the way, we now know you can build this as well. The science you can do in water or in ice. the advantage of ice is the logistics is simpler, even though, you know, it's not that simple. So it's easy for me to say that logistics is simple. But there was a man, he passed away, unfortunately, Trevor Weeks, who gave me the answer to that question. He said, you know, this is astronomy. The sky is big. It's not like building an accelerator where you have one experiment, you detect the Higgs, measure its mass, and you win. So astronomy is not like that. You can have a much smaller telescope and have the right idea of looking in the right place or doing the right analysis and make a major breakthrough. So I think more experiments are critical. Also, and I don't think this came through in this talk, but you know, we always live in panic of announcing something that we later have to take back. Because we are only instrument, if we have to take something back the next time, nobody will believe us. So it would be great, actually, to answer the question of these fluctuations by just asking the people in the Mediterranean, go and look at HJC 1068. And in fact, they have, by now, they're building this experiment, and they have already confirmed our diffuse flux from outside the universe. And Baikal has analyzed a couple years of data, and their highest energy event comes from, guess where? TXS 0506. So, but you know, where you get a flavor. This is astronomy, so it's not like building one accelerator with two experiments or one experiment. It's different.
I'm going to take a question from a Zoom participant, John Grunsfeld. He asks, what about neutrinos from the sun?
Yeah, that connects with the question about neutrinos from the Big Bang. Okay, so I have to... Neutrinos are difficult to detect, but the higher their energy, the easier it is to detect them. So we look for neutrinos and do astronomy where it's easy. Looking for neutrinos from the sun, you have many more of them, but they are lower energy. So in an absolute sense, they are even more difficult to detect. And we wouldn't detect them, just like the ones from the Big Bang. But there are so many of them, so that makes it possible anyway. And so this is like it's both, each energy range is like apples and oranges. You use techniques that are just right for that energy of neutrino you want to look for. In fact, in our case, we should be proud of that. The highest energy neutrinos we have detected by now had an energy of over 10,000 TeV. But the lowest energy neutrinos, like from this source, are 10,000 times lower energy. So we detect neutrinos of a very long energy range. And we have a separate experiment buried in the deep core of ice cube, where we detect GeV neutrinos and do the same physics as Fermilab at somewhat higher and at 10 times higher energy, which makes it interesting. So again, it's an example of if you target an energy range, you have to target it and develop a technique that's just right, because they're so hard to detect, right?
Before we go to the red microphone, I have a question, which is, how did you calibrate these detectors when they're already in the ice?
That's a great story. First of all, the answer to the question is you calibrate them by measuring the atmospheric neutrino flux. We know that flux. Okay. It's seen by lots of experiments. We can calculate it. And so we, you know, experimental friends will tell me, no, we measure the flux. And I say, well, we calibrate the detector, and we are both right. But we detected an event a few years ago, and I didn't talk about it, but it's made by a neutrino not interacting with a nucleus and making a nuclear interaction. It's a neutrino that interacts with an electron. And it makes a weak intermediate boson, like, you know, at the particle physics lab. And that weak intermediate boson has a mass of 80 Jeff. So that neutrino, to make that weak intermediate boson, which we clearly see in the detector as something different, has to have an energy of 6,300 TeV. And that's exactly what we measured. No tricks, no changes of parameters. We just applied our techniques and got the energy right. And I am very proud, because it took about 2 months before I realized, hey, we finally calibrated our detector. Nobody else had thought about it. We're so excited about seeing a W in the ice, right?
How much variation was there between the detectors?
No, you get one energy measurement, right? And the precision was like 6,300 TeV, 15% error, which is like a respectable particle physics experiment in a lab.
Red microphone.
Daya Ahmed, physicist.
Could you please hold it up close to your mouth and speak?
Daya Ahmed, physicist. You speak about neutrino, but do we know what kinds of neutrinos?
Yeah, I didn't talk about that. Of course, we can always tell, you can tell, Nui, I'm now going into the 3 flavors, right? Mm-hmm. Nui, nu mu, nu tau. So most of astronomy is done with nu mu, so I only had to mention for our 2013 discovery this big Nui and nu tau events. But what happens is, if you see neutrinos from very far away, they oscillate. But in this case, their energy is high, they come from very far away, so the flavors actually separate. These oscillations stop, and you see 1/3 Nui, 1/3 nu mu, 1/3 nu tau. And our data is totally compatible with that. Now, that's a measurement which we are going to do with much higher precision, and this 2025-26 upgrade is to do that measurements with high precision. Because if you see a deviation from 1/3, 1/3, 1/3, you've discovered new physics. New neutrino physics, which in a sense we already know to exist, right? Because they have this tiny mass. But it would be nice to actually study and get more hints about the new physics. And so flavor oscillations is a big priority in these experiments.
Does their energy correlate with their flavor?
Well, we do this experiment in 2 ways. The way I just described with cosmic neutrinos, but we also do it with atmospheric neutrinos. We don't have as good an experiment as the experiments at Fermilab, but we have many more neutrinos. And so we are about to publish an oscillation result in the energy range of Fermilab, a bit higher, which contains 60,000 neutrinos and 6,000 nu taus. And so this is a whole new game of precision, but we are still working on that. You should realize that only a quarter or so of the people in this experiment are working on what I talked about. This is like a Disneyland for doing all kinds of things. Like, I could go on, we have the highest precision measurement on violations of special relativity, for instance.
Could you say a little more about that?
Yeah, that's well, what you do is you actually look whether neutrinos, that's the simplest way of answering your question, neutrinos of different energy travel with different speeds. You know, first approximation, they all travel at the speed of light, right? In this experiment, everything is, and so you start, what you measure is the relation between the energy and the momentum, and see if it satisfies Einstein relativity that you learn in elementary physics. E square is m square plus p square. Yes, it does. We have a limit on the change from the velocity of light of 10 to the minus 28.
That's pretty good.
It's not that difficult, actually. You just have to have the right experiment. Yeah.
Are there any other questions? We have somebody point, blue microphone. Yes, we are calling on the blue microphone.
Hey, so I'm Sean, and I'm not a member. I have a question about the extragalactic neutrinos you're talking about. You mentioned that they're coming from the center of a blazar. How close to the event horizon, like an estimate, like 10 parsecs, a kiloparsec?
Less than, you know, of course, this is under debate, right? And there's no precision in this business, unlike the 10 to the minus 28. But it looks like tens of Schwarzschild radii, less than a parsec. And if that's really where the action is, then it will be tough. We'll have to do it with neutrinos and with some telescopes like ALMA, for instance. And of course using radio detectors. You know, you all know the picture of the black hole in radio, right? To things like that. By the way, these radio telescopes have made a picture of the central engine of TXS 0506, and what you see actually, which got us on the path that it was all acting in the core, you actually, after 3 or 4 parsec, you see the jet disappear. It diffuses. So it's not a jet that's making the neutrinos. It fooled us. It's happening in the core, maybe at the base of the jet, but in parsecs or less.
Red microphone.
Hi, Brett Magrum. I'm a member. Since these detectors are frozen in the ice, from what you've said, I was curious, have any of the detectors failed? What's your fail rate on detectors, and how would that impact, you know, the experiment going forward over decades?
I was dying to hear that question. You know, I said you get a stable detector, right? I can tell you, so we've lost a handful of the 5,000 plus. And when we lose a photomultiplier, it's like a funeral. And we study it because, you know, if you apply statistics to the number we lost, this will last thousands of years, these experiments, like the pyramids. But it's like, you know, if you apply that to me, at my age, I will live 400 years or more. But you die by systematic effects. And so you study whether the electronics, you could get a glitch in your electronics that, you know, destroys all photomultipliers in a few months. I think this is very unlikely. But yeah, this is the great advantage of this ice. The stability and the longevity of the detector, I don't think the water detectors can ever reproduce this. On the other hand, that doesn't matter, right? If we lost 500 phototubes tomorrow, it would not matter. Our precision would not change. So it's also very forgiving. And in water, but they can of course replace their strings, we cannot, right?
Any other questions? If not, we'd like to thank you very much for sharing your time with PSW and sharing these results.
Thank you.
And before you go, I'd like to present you with a small token of thanks for the time you spent.
Thank you very much.
Volume 1 of the Bulletin of the Philosophical Society of Washington, in which you will find who the founders were, why they founded the organization, and why they called it the Philosophical Society when they weren't doing philosophy, they were doing science.
It's a great honor to be invited here. It was a great pleasure. Thank you very much for the invitation.
Before everyone goes to the social hour, or wherever, we have a few important notes. The next meeting, number 2467, will be on November 18th. The speaker will be Tony Levy. Tony is professor and chair of electrical and computer engineering, electrophysics at University of Southern California. He will be speaking about a new technique for seeing inside anything in 3D called micrographic X-ray laminography. I actually picked this because I like that title so much. The lecture is sponsored by PSW member Adarsh Deepak. The 2468th meeting will be on December 2nd. The speaker will be Sean Gulick. Sean is at the University of Texas, where he is a research professor in the Institute for Geophysics, co-director of the Center for Planetary Systems Habitability, and associate chair of Lithosphere in Deep Earth Studies. And he'll be speaking about the latest on the great dinosaur extinction. The 2469th meeting, which will be the last of the fall 2022 lecture series, will be on December 16th. We'll have two speakers, Rachel Klima and Wesley Furman. Rachel is planetary geologist and director of the Lunar Surface Innovation Consortium at the Johns Hopkins University Applied Physics Laboratory, and Wesley is senior staff scientist at APL. They will be speaking about the Lunar Surface Innovation Consortium and about going back to the moon to stay. Please check the PSW website often for up-to-date information on meetings. And finally, let's thank tonight's crew, James Heelan for reading the minutes, Robin Taylor, who you never see because she's hiding behind all the instrumentation back there, who does the video, the sound, the live stream, the Zoom, and arranges the dinners. Jared McQueen and Connor Nixon for running the cameras, Ann McQueen for YouTube chat and rosettes, Cameo Lance keeping the room in order, and Bill Mitchell hasn't done anything yet, but will be editing the video prior to its permanent posting on our YouTube and Vimeo channels. And with that, I will now adjourn the 2466th meeting of the Society to the social hour. I wish everyone a good morning, good afternoon, good evening, or night, wherever you happen to be. The meeting is adjourned.